This next example is in honor of the Titan submersible. And if you don't know what that is, you can Google that. It exploded. It was tragic. People died. One wonders if they were being completely logical with their risk-taking, but it was still sad that they died. Okay, so here's the thing. If something explodes in the ocean, and let's give it 6 sensors that all pick up the sound of the explosion, can you use that to figure out where the thing was when it exploded? Well, it's making an assumption here. I'm making an assumption that the speed of sound is the same throughout the whole ocean, and that's not true. And it depends on a lot of factors like temperature, depth, and stuff like that. I'm just going to pretend like that doesn't matter. And I'm just going to assume that we have 3 dimensions to work with and that we could reverse engineer naively where the Titan was when it exploded if we have enough sensors telling us when they heard the pulse. Secretly, I know that this Titan was at position 111 at t equals 1000, and the speed, meaning the speed of sound in the medium, is 0.5. So if I use the reciprocal as 2, it takes whatever this distance is times 2 is going to be how many seconds later I'm going to hear the pulse, for example. It's whatever units you want to use. Okay, so those green numbers over here are all the recorded data. We're going to assume we know where each of the 6 sensors is and the time at which it heard the pulse. What we don't know is this stuff in blue. We don't know where the Titan was, and we don't know the time it exploded, and we're not really sure of the speed of the propagation of the wave, of the sound waves either. Okay, so that's how my model is going to work. And along these red lines, I'm going to put a function that says, in terms of these variables x, y, z, t, and the speed reciprocal, the 5 variables, so 5 dimensions, if I have that, I can predict at what t hat, I just put t prime, but it's like t hat, that's the predicted time at which that pulse should arrive, given that I actually know the location where each sensor is. And then the green time variables, like over here, this green time variable, that's telling me when I actually receive the time pulse. So this is the predicted time pulse, is the ones we're going to calculate off of our, as we are optimizing x, y, z, t, and speed. When we're optimizing that, we're going to see how far off the t is from the t hats or the t primes. And then we're going to see if we can figure out, see if we can get the algorithm to tell us where the Titan was, what time it exploded, and what the speed of the traveling wave is, the sound wave. Okay, so here's what the code looks like. It has the same components as our last code. We start with our imports and we start to build our sheaf. So we label our 6 cells as S1, 2, 3, 4, 5, 6, and each one has dimension 1. Those are the estimated time of arrival of the pulse. And the Titan has 5 dimensions because it has a location, explosion time, and I could have put the speed in the model somewhere else. I'm just putting it there. It could have been anywhere. It doesn't really matter. So I could have made this 4 dimensions and just hardwired the speed of the wave. That's fine. And one of the tricks I use when I write these is I'm going to just make these guys variables so that my code is easier to read and it's easier to change something. But these are not going to change. These are variables that are holding constants, let's say. It's constant for the whole run of this code. All right, so I'm going to go ahead and create all these estimators, which is all I'm doing is I'm saying what is the distance between x, y, z and this point, and whatever that distance is, I'm going to multiply by the speed reciprocal and tack that on to this, in this case 1000, or whatever t happens to be, and that's going to tell me t hat. That's how I'm getting t hats. And then I'm going to go ahead and graph this to make sure it looks right, and all the data I'm putting on the cells are actually just these green ones. Okay, so this green t values, I'm just putting those directly on the cells, and I'm not allowing that to optimize. So You could have a different model where you don't know where one of the sensors is, but I know where all my sensors are in this model, and I know what all the times are. Okay, then what am I going to do? I'm going to maximally extend, and similarly to what we had in the last case, we can blank out all of these. We don't really care. We're only propagating information from the Titan outwards, so we really only need to maximally extend Titan. And then I'm going to look at my consistency radius that I'm starting with, and then I'm going to allow the algorithm to optimize on the Titan variables, and then I'm going to ask it to do its sheaf magic and then see what happens. So let's see if this works. Okay, so I started off with a less good arrangement with a consistency radius well above 0. And you can see I put this bogus data in here. That is not the correct answer. And let's see if it gets the correct answer that I told you it should be. So I said the answer should be 1,000 with a reciprocal of 2. Okay, so I have 1,000 and 2. Yes, we got it. Yay! All right, so you can just play with this. You can just take this code and change out, see how bad this can get before you can't find the Titan anymore. I don't know, I'm just making things up. I'm literally just making this up. Save that and run the code and see if it works. And okay, it does not look good. All right, so bad. Okay, but maybe I went too far. So this is the fun thing to do. You can go ahead and play and say, well, is it just because I need to change one of these things around? Maybe I'm asking too much. Let's get closer to the solution and see how close we need to get before it'll actually converge. But there we go, it's converging again. So it just kind of gives you an intuitive feel for how far away from the solution you can go and still land on the solution. So hopefully you can have fun with that one.